Okay, thank you very much, Gennaro. I just wanted to check. I'm still coming in loud and clear.
Yes.
Excellent. So thank you very much for that introduction. And I also thank the Calgary section of the Canadian Geotechnical Society in providing me this opportunity this evening or this afternoon, depending where you may be, to share my experiences and thoughts concerning testing in geotechnical design. So the presentation first talk about the role of geology and geotechnical engineering, quickly discuss the geotechnical design process, in particular, a concept that I call the geotechnical circle concept, which is a framework of linking geotechnical testing, whether it's in the laboratory or the field, along with theoretical considerations. Provide some of my thoughts with regard to empirical correlations, present some geotechnical testing applications, and end off the presentation with key messages or things that I would like you to take away from this evening's presentation. Almost 90 years ago, Carl Terzaghi wrote in a paper that it took me 2 years of strenuous work to discover that geological information must be supplemented by numerical data, which can only be obtained by physical tests carried out in the laboratory. I think this is one of the first statements in terms of the importance and role of, I would say, laboratory testing, but I would also extend that into field and in situ testing. Carl Terzaghi and many other geotechnical pioneers always based their work on the background of geology, and they stressed the importance and necessity of linking geology and geotechnical engineering. Leggett, another example is Robert Leggett's book in 1962, Geology and Engineering, in which he discusses the important interrelationships between geology and geotechnical engineering. If you've not had the opportunity to read this book, maybe not all in its entirety, but certainly some selected sections, I think you will find it to be a very interesting and informative read. And as I mentioned in my CGS Hardy address last year, statistic, probability, and reliability are useful tools if properly applied, but they must not become a substitute for understanding geology and geological depositional processes, fundamental ground behavior and theoretical conditions, failure mechanisms, and engineering judgment and experience. This slide presents what I call the three legs of a very stable stool in geotechnical engineering. The three pillars or legs of the stool are the geological model, the ground model, and the geotechnical model. And there's a number of arrows here that sort of show the interaction between the various models. One thing I note, this is a paper Wang et al. In 2019. They put laboratory testing down here in the laboratory and field testing down in the ground model, and I think that's fine, but I think it also fits into the geotechnical model. I've presented this slide many times in past presentations, and I thank you for your tolerance in letting me present it again, but I think it's a very illustrative of the geotechnical design process, regardless of whether it's dams, bridges, or buildings. This one happens to deal with a building, and it starts off with, you know, the design criteria clients needs, then what is the design issue, in this case, what type of foundation. And that's generally design controlled by codes of practice or manuals of practice, and they provide insight into your site investigation requirements, which through interpretation brings you into the ground and geotechnical model. It also provides guidance on the calculation or analysis model, which then feeds into your geotechnical model and geotechnical analysis and design. And obviously testing plays a key role up in here in terms of the doing tests to obtain engineering properties, but there's also testing that confirms some theoretical formulations, and testing also comes into the load effects. So testing plays a very key part. And when that input is put into your analysis, etc., and you get a result and you apply appropriate engineering experience and judgment, you will then select what the appropriate design parameter, or what the design would be, or in this case, a footing. So testing is embodied in the design process. So this slide summarizes, I would say, key considerations in support of any design approach. And there are things such as understand the interaction between the geological setting and the ground and geotechnical conditions. And in my view, this is very important, and I think can be more important than methods of analyses and calculations, because no matter how sophisticated your analysis and model may be, if you don't have the facts and conditions correct, then the output from your model is perhaps not that meaningful. As geotechnical engineers, we have to make the most of a limited site investigation, because we don't always get to do all of the things we would like to do. And when you get test results, it's important that you honor all the data. What I mean by that is, if you have outliers or something in your test results, you can't just dismiss them because they're an outlier. If you double check your test procedure and your interpretation, and you're convinced that the data point is correct, well, then you must honor it and keep it. Thing that I tell my junior colleagues, as I remember many decades ago when I was a junior engineer, I always wanted to rush into analysis, but my message here is to spend time to make sure you establish an appropriate geotechnical model. This feeds into what I said earlier about facts and conditions. And so take the time to get the record of borehole and laboratory testing data, correct your cross sections and things like that, because at the end of the day, that is what you will be judged, is the accuracy of your the model based on your record of borehole and other information. I think it's important you capture the essence of the problem and understand what the key controlling design issues are, and then you proceed with simple testing and analyses, and only followed by increasing level of sophistication as is needed. It's also important to have a consistent theoretical framework in which to assess, interpret, and interrogate the test results. Myself, I've always worked in terms of critical state soil mechanics and yield envelope effective stress paths as a framework. I think if you have used it or know of it, you will find it useful, but there's other frameworks in which one can work. But the important part here is that you need to have a framework or theoretical considerations in mind to appropriately assess, interpret, interrogate your test results. And then finally, good engineering and judgment experience is always important. Because as they say, good judgment is usually the result of experience, and experience is frequently the result of bad judgment. Going back to Leggett in his book, Geology and Engineering, he discusses three primary branches. And at that time, he called it soil mechanics, but we now refer to it as geotechnical engineering. And he has three subsets or branches. One is theory and theoretical approaches. Another branch deals with site investigation so that you can get good quality samples that are representative of the in situ condition. We typically refer to these as quotation mark undisturbed samples. And the standardization of testing, such as the standard penetration test and field Vane test. And then there's the laboratory testing on the samples that I just mentioned above that you obtain from the site investigation work. So in situ testing, such as the CPTs and pressure meter testing, dilatometer and others, were developed and occasionally used starting in the 1980s. I remember first running across that at early start of my career, and now it's routinely used since about the mid-90s. And there certainly has been an emphasis on relying on in situ testing. And I think sampling and laboratory testing has taken a bit of a background or put in the back burner for a period of time, but my experience on working with the projects and that over the last few years is laboratory testing, as I say here, appears to be making a comeback. I think people are, when I say people, us in the geotechnical community are realizing and reestablishing the value of high quality laboratory testing. And Leggett's comments about those three branches, the theoretical considerations and that type of thing, fits into what I call the geotechnical circle concept, is where you have a relationship between laboratory testing, constitutive laws, results of in situ testing and theory, and then the results feed back, and there's an iterative or a circular approach. Or the other way of looking at it is sort of like a layers of an onion, where you are starting from the outside, working in, understanding the project needs, developing a site characterization program, and then setting up testing conditions that feed into field testing and also into site assessment and design. For main purpose of this slide, because you may not be able to read everything because of the how many words, but it's really to demonstrate that testing, it's an iterative process. And I've already gone through the upper part of this particular series, where you need to understand the requirements and then define your testing program, review existing site information, develop your conceptual geotechnical model based on your geological and understanding of a site, and design your testing program. You collect and analyze your data, you interrogate it and see how it fits with your theoretical framework, and if everything is consistent, then you're ready to report your results and establish your model for geotechnical model for use in design. If not, then you go back and do some more work, or maybe it's necessary to modify the the program completely, and you continue this particular loop until you get to the answer yes at the bottom of the slide, and proceed from there. I have a few key messages about what I consider constitute a meaningful or value-added test programs. First one of this is that it's important you understand the advantages and limitations of the various tests, whether they're in the lab, field, or in situ. The next one is basically, you know, you need thoughtful and adequate planning to, you know, which is based on a good understanding of fundamental ground behavior and work within that theoretical framework. The third bullet here is really, you know, what you get out of a testing program and how valuable it is commensurate with the degree of thought and attention that you put into the program. So, you know, frankly, if you don't put much effort into thinking about it and that, then you should not expect too much back. But if you think carefully and understand what the role and purpose of each test is, then you end up with a meaningful program results. It's important to simulate the in situ and loading conditions to the best and fullest extent practical. An example of that would be, you know, testing in your field stress range, or if your pore water has salinity and things like that, then you should try to match that in your laboratory testing. The results are only as good as the sample and care taken when performing the test. So if you've got a really obviously poorly disturbed sample, I mean, don't waste time and money trying to test it because the results, you know, as I said, they're commensurate with the quality of the sample to begin with. Poor quality, poor results. A lot of people think lots of data is a good thing, and it's not necessarily so. I would tend to provide more emphasis on quality rather than quantity. I've already mentioned about don't ignore the outliers. And it's important to use statistical reliability methods in terms of building up a geotechnical database for understanding mean value and coefficient of variation. And my last bullet is quality is everyone's responsibility. So whoever is involved in the testing program in the field or in the lab or whoever, everyone should be doing their best. So I'd like to now talk about examples of testing supporting the development of theoretical considerations and applications in practice. And a subset of this, or a side thought, is that high quality, good test data results, they stand the test of time. First example of this is the state parameter approach, which I think everyone is familiar with, and it's very important for the fundamental understanding of sand behavior. It was developed in the 1980s with work by Mike Jefferies, who was with Gulf Canada at the time, and then Ken Bean and others from the Golder Calgary office. And just briefly, the testing revolves around traxel testing to establish the steady state or critical state line. And then you have a in situ state, which call A, and the state parameter is the distance between your in situ state and the critical state line. If you lie above the critical state line, you have positive state parameter, and if you lie below, then you have negative state parameter. Positive state parameter identifies contractive soils, and negative state parameter dilative soils, and all of this. The key part of this understanding was to make it applicable to the field of, and that was developed through the use of CPT, cone penetration testing, to the results of using tip resistance and other parameters would give you state parameter. And then typically now it's recognized that a value of state parameter of negative 0.05 is typically the boundary between contractive and dilative material. But again, this was developed on the basis of testing and having a good theoretical framework in which to operate and interpret the test results. Another example is yield envelopes, which provides a consistent framework for assessing clay behavior. This plot I've plotted it in terms of axial minus radial or vertical minus horizontal stress, so that most of the time if you have a positive K naught, you're up in this zone, but if you have negative, or not negative, if you have values of K naught greater than 1, then you're down in this zone, which becomes negative because the radial stresses are greater. But establishing the testing to establish a yield envelope is very important. If you, with your stress state, if you're basically staying within your yield envelope, you're in an over-consolidated state. Strains tend to be small and tend to behave more elastically, but once your stress level exceeds the yield envelope and you're on the other side of it, then you're in a normally consolidated state where you have higher compressibilities and other factors, in a decrease in coefficient of consolidation and many other factors. So if you could track in the in situ based on piezometers and other things and actually develop field stress paths, it goes a long way in terms of understanding your state of stress in the soil and where it is with respect to failure. And it's recognized that the average mobilized undrained shear strength is basically controlled preconsolidation pressure. I think most people are all familiar with this slides. This upper diagram shows that a slip surface to an embankment, you have certain portions here where this is traxial compression, then more into direct simple shear and extension. And typically for soils, it's recognized that 0.22 times the preconsolidation pressure gives you a good value of average mobilized undrained shear strength. This value came out of the work at Laval with Tavernas, La Rochelle, Serge Louet, and others were based on the St. Albans test fills, but also Mesri in the early 80s also theoretically developed a relationship, and his number was 0.23, which is close to 0.22. And this relationship also fits into this equation, which really is the Shansep equation, where your undrained strength ratio with respect to effective stress is a function of your normally consolidated strength ratio in OCR. And this plot on the left is just the ratio of SU over preconsolidation pressure. Traxial testing, the triangles here, typically in the range of about 0.3, direct simple shear in around 0.2, 0.25 type of thing, and then extension tests. Of interest to note is the field Vane tests, which skirts across the, well, not cross, up and to the right, and it's a function of plasticity index. And important observation is that if you're in the plasticity index of the 20 to 40 range, then field vane tests will be close to your direct simple shear motor, which is the average, close to the average mobilized undrained shear strength. A few comments about direct simple shear testing. The constant volume direct simple shear testing is probably the most commonly used now in state of practice. But it's important to recognize, or I think it's important to recognize, that constant volume direct simple shear tests are not truly undrained tests. I think many people, and I used to think that they were undrained tests, but they're not. They're a proxy to or equivalent to an undrained shear strength, and that's on the basis of constant volume. And in most apparatus, pore water pressure is not measured, rather it's inferred based on the change in applied vertical stress to maintain a constant volume. And that's taken to be equivalent to the pore water pressure. So this is a bit of a pet peeve of mine. So if you're reporting constant volume direct shear test results, I see sometimes in reports measured pore water pressure, and I think, and maybe people will say, Dennis, don't be so pedantic, but it's important to realize that this is inferred. It's not actually measured. What was measured was the applied vertical stress to maintain constant volume, and through effective stress equation, that is interpreted to be the pore water pressure. The other thing is saturation in constant volume shear tests can be and often is less than 100%. You don't necessarily have to saturate your sample to have meaningful results. But it's important to understand that there has been comparisons between constant volume direct simple shear and truly undrained direct simple shear, and the conclusion from that is, for all practical engineering purposes, the results are equal. I'd like now to share some thoughts about the empirical correlations. Geotechnical engineering is embodied with the use of empirical correlations. They're very much a part of our history and tradition, and they're very useful, but you need to understand the basis of development and limitations. And I think you should only use those that capture the essence or the first order controlling effects, and that'll become more clear in subsequent slides. And you should have a theoretical basis or a physical understanding of what properties you should expect to be related. Like, why are you correlating this value with this value? I think it's important to correlate undrained response to tests that are undrained in nature. And same thing, if you want drained parameters, you should correlate them to drain responses. I see many correlations where it's an undrained test and you're going to drain parameters such as effective friction angle, and perhaps the values look all reasonable, but I think there's a bit of a disconnect in terms of taking an undrained test and then going and saying you have a drain parameter. And it's also important to consider strain compatibility in terms of the deformations. An example of this would be the dilatometer, which applies a very small strain displacement to the soil. I think it's appropriate for values of K0, let's say, because it's that small strain. And even though the correlations may be consistent with others for large strain behaviors such as undrained shear strength, but you have to keep in mind it's a correlation, and you're using a small strain test to predict or estimate large strain behavior. Example of that talk about is the field Vane test about controlling the first order effects. And everyone's quite familiar with the field vane, but it's important that 90% of the failure surface is on the vertical plane, and therefore the strength should be controlled by the horizontal stress regime, but most correlations use vertical stress. And this plot is something I developed a long time ago, but like I said, good test data stands the test of time. And the plot on this side is the normal SU vane divided by the vertical effective stress, and you get this type of shape which supports the Shansep concept. But for particular sites where I was able to measure K0 in that, and so I could normalize the vane strength with regard to mean effective stress, or it takes K0 into consideration. And when you plot this same test data here just against vertical stress, and you do it against mean stress, you get this very tight correlation. And I think that is an indication that, yes, you're now starting to capture the first, controlling effects. And for the field vane test, it's the horizontal stresses that really are controlling the strength. This plot sort of reinforces that. I had already mentioned this with the field vane tests coming along like that. And then if you have at a certain plasticity index, it's the correction value is not too much. And this is the basis of actually the Becker correction factor that accounts for high plasticity clays to reduce their value so it fits more so in with the mobilized average shear strength ratio. So the same plot data here is then plotted on the right-hand side of this plot, but instead of preconsolidation pressure or vertical yield stress, it's in terms of horizontal yield stress. And again, you can see the scatter in the data is very minimal now, and which to me supports that this my hypothesis earlier that it's horizontal stresses that are really controlling field vane strength. So preconsolidation pressure and OCR are very dominant controlling factors on clay behavior, and there's many correlations related to preconsolidation pressure and OCR, but that requires a reliable and unambiguous assessment of preconsolidation pressure, and many soils have called a rounded E log P curve, and if you apply the typical Casagrande type of interpretation, it's very difficult to determine the point of minute maximum curvature and estimate the preconsolidation pressure. So you really need a more definitive assessment of preconsolidation pressure. And this work led out of work that we did in the Beaufort Sea in the early 80s, where Beaufort Sea clays had a very rounded E log P curves, and it was important to come up with a more definitive assessment. And at that point, developed the strain energy, or the work done on the odometer test. And it wasn't that I woke up one morning and say, okay, let's do something innovative and unique today. It was rather I was in the lab. In those days, we did a lot of our own testing and running a series of consolidation testing and Traxel testing. I was reading some papers on strain energy, and they were by Jim Graham and Francois Tavenot and others, and they were determining yield stress in triaxial, which has 3 dimensions. And I said, well, if they can do it for 3 dimension, let's see what happens if we just do it for 1 dimension. And what came out of that is the same test data and this E log P curve plotted against work done yields a very clear and distinctive preconsolidation pressure, which then is very important when you develop your correlations. And I have to say, without to blow my own horn or anything, but one of a rewarding time in my career was when Professor Charles Ladd at MIT called me, and he says that they now routinely use this approach in all of their research work. But anyway, enough of that. I'll just say, if you haven't used this approach, I encourage you to do so, and hopefully you will find that it is meaningful and informative. It's important to understand, I was talking about the effect of horizontal stresses and that. And so again, work in the Beaufort Sea with pressure meter testing, which is on the right-hand plot here, where we, from the shape of the curves, we can determine yield stress, etc. So again, in terms of in the lab, what can we do? What can easily be done, practically be done? And so if you take a sample and you have this tube, and this lower one here is the what I call horizontally trimmed samples, the normal consolidation tests. So that gives you vertical stress. So the thought was, well, if it trim it vertically and then test it in the conventional odometer test, that should give horizontal stress. And so this plot is shows the relationship for a site in the Beaufort Sea here, Malacca, where the squares are the results from the pressure meter testing, and the circles are from the odometer test trimmed on vertically trimmed samples. Now they're not identical, but they sort of show the same shape and profile. You notice here's an example of an outlier that I couldn't dismiss, so I had to keep it in the plot. But the point here is that just thinking about the stresses, from a practical sense, and using simple laboratory testing, you can get an assessment of K naught. It's well known that preconsolidation pressure you can get from tip resistance, the classic equation where the preconsolidation is a function of the tip resistance minus total vertical stress, and typically F varies from 0.28 to 0.33. But this plot again was in the early days of we're working on projects in which it was fortunate to have pressure meter testing and lots of odometer tests and CPT tests. And each one of these particular points was a direct correlation in terms of interpretation. So if the OCR was interpreted from the odometer tests, and then the tip resistance, normalized tip resistance. This plot here, rather than the normal vertical effective stress, it's again plotted in terms of mean stress, so the effect of K naught. Now this shape is very similar to what we have if you plot this in terms of vertical effective stress. But from this, the observation that this factor F in terms of this equation here of tip resistance minus vertical stress is a function of K naught. And this upper one that is typically used and reported in the literature is fine if you have your sort of normal range of K naught. But once K naught, if you have situations where K naught is higher, then this particular value drops. So this is a useful correlation, and which captures what I consider the controlling effects or the controlling orders of the what control the behavior. Coming back to the field vane, where we typically come up with an NK factor to use so that you can use your CPT tip resistance to calculate undrained shear strength. And I think everyone knows and realizes that this value of NK can vary from considerably down from just a bit above 5 up to about 20. This plot shows it related to K naught. So if you're in your normal range of K naught, you tend to have these values that that are you probably would recognize in your own practice of values of K naught, values of NK. But if you're working in higher K naught materials, then this NK value can increase. And the bottom figure here shows the relationship with between OCR and K naught. And so it's showing that the NKT is relatively insensitive to OCR because it's plotting here all of these symbols are more or less in a line, but these are values of K naught in the order of 0.8 to 1.4. And again, you'll see these are sort of your typical numbers that you have for KT. Maybe it's 13, 14 that I think many of you probably have used in your practice. But again, this is the point to show the some controlling factors with regard to the horizontal stress regime. So talk a bit now about field performance testing, such as full-scale pile load tests and those types of things. And this testing is essential for design improvement and to make your design more efficient. And especially for what I call geostructural elements, such as ground anchors, piles, and ground improvement technologies. And the testing is also plays a key part, obviously, in QA/QC programs. And the commonly used tests for these are those that we're all very familiar with, but we can add pump tests to it and geophysics. I think a lot of geotechnical characterization programs could benefit from the maybe more use of geophysics, and not only downhole, but just seismic or surface seismic waves to assess, to get a better sense of your ground model. And then there's full-scale field performance tests, and then there's physical modeling tests such that are on a bench scale, such as a centrifuge. For full-scale field performance tests, they provide an improved understanding of the soil structure, geostructural system. They certainly provide a design efficiency because you can, with testing in that, use higher geotechnical resistance factors in LRFD or lower factors of safety. But it's important to realize, though, that if you want to refine your design, you really have to take your load tests to failure so that you obtain the ultimate values of the geotechnical parameters for a pile, whether it's skin friction or end bearing. Because it's once you know the ultimate value is when you can refine your design. If you don't take your test to failure, then really it's only a confirmation or proof of design test, but it doesn't allow design refinement. It confirms that your design parameters are okay and you get satisfactory performance for the test range stress that you considered. And you will have a higher degree of certainty of doing a proof test. But if you want to refine your design and have the highest degree of certainty or reliability, taking your load tests to failure is the way to do that. Certainly, people recognize the figure that's O-cell testing for caissons or drill shafts. And the codes, as most people know in the call, you can increase your resistance factor from 0.4 if it's only based on static analysis up to 0.6 and now even higher for full scale tests. So that's a 50% increase in your pile axial resistance. But you have to keep in mind that that doesn't necessarily translate into 50% of cost savings of the overall system, because there's other factors such as pile spacing and redundancy that need to be taken into account. So you would reduce the number of piles by having a higher resistance factor, but the total cost savings is not commensurate with the increase of going from 0.4 to 0.6. And so field performance tests are expensive, but they're, they can provide significant cost effects. So an example of that is the upper part here of without a test. I'm fairly confident with the line that I've drawn here that is solid, but then the dashed line reflects that I'm estimating that this is what the ultimate shear axial compression resistance will be. And then if that's all you do, you would multiply that by 0.4 to get your design value. Now, if you actually did the full scale test, and in this particular case, the measured value is higher, and you then get to take 0.6 of that value. So you've ended up with a substantial increase. But I want to caution people. Most people say, well, maybe we need to do more testing. But implicit in that statement is they think you're going to get higher values. But you have to be prepared that your testing may produce a lower value than what you expected. But once you've done the test and it comes in lower, you have to live with that test, because I've had clients approach me and say about doing this test, and I'd say, well, are you sure you want to do it? And they say yes. And occasionally it comes in that the results are lower than what we thought they may have been, and they were disappointed. But even though they're disappointed, they understood that they've done the testing, so now you have to work with that particular testing. So I make that comment just as a practical thing, because as I said, a lot of times in my experience, people do more testing because they feel they're going to get a higher number and therefore their design can be more efficient. Physical modeling tests, they're needed because the complex nature of the ground can't be captured sufficiently by analytical and numerical methods alone. And so they provide an improved physical understanding of the key failure mechanisms and deformation, and assist in assessing the construction processes and soil structure interaction, and also assist in calibration of analytical and numerical models. Typically, these tests are done at 1G, basically because of cost and budgetary considerations, and they would do that largely, maybe on a group of model piles that are, centimeters long as opposed to meters long, and those types of things. So they're largely used in research work to complement or supplement new numerical modeling, and they have limited use in practice except for some, I would say, large special projects. Some examples of physical modeling tests I already mentioned about single and pile group behavior, including static and cyclic loading. Frost heave forces on pipelines in Calgary. We have a cold room, and we can test large scale setup with pipe and frozen soil to measure that interaction. We've done work with iceberg scours studies, flume testing for tailings deposition. There's some recent work being done in terms of better understanding dams and overtopping of dams and fuse plugs by the use of physical models, and also the centrifuge. The centrifuge has certainly increased its use over the past 25 years. It has many advantages in terms of producing a higher stress field, that helps model the actual stresses that the pile would feel in the ground. In terms of effective flow, that it has the advantages of significantly reducing the modeling time to assess your effective flow. Again, it has, at this state, I think there's limited use in practice unless you have a very large project, but I certainly was fortunate to get a chance to see how the benefits of the centrifuge testing. And those of you who attended the last in-person conference in St. John's, and if you were there, will recall that I related a story where Jack Clark chastised me for my skepticism of what the centrifuge could do. And he was an advisor on the Confederation Bridge, and certainly it did help us with our improved understanding of failure mechanisms, especially for the footings that were subjected to very high ice loads, which resulted in high load eccentricities and inclinations. But it was important, the value that I took away from it, it helped identify when simple 2D finite element analysis was sufficient, or when it was necessary to get into much more sophisticated 3D finite element analysis. So I thought the interaction of theory and the results from physical testing, it was certainly very useful. So last couple of slides here. I'm not sure how I'm doing on time. Yeah, probably run over. So understand the important relationships between geology and geotechnical engineering. Testing is an integral part of the design and is used in the geotechnical circle concept. It should not be, testing not be done in isolation. Again, meaningful and value-added testing programs require careful and adequate thought and interpretation within a consistent framework. High quality test data results stand the test of time. It's very important to understand the limitations of tests and which tests are applicable. Use and develop correlation that capture first order effects. Again, undrained test response should be used for undrained parameters. And my final takeaway message here for you is that if you want to refine your design, and that it's important to take your field performance test, pile load tests to failure. Thank you very much, and sorry for running over time, but once I get started on this particular subject, and since I can't see everyone in the audience, I can't take hints that it's time to stop. But anyway, I have stopped. And willing to take questions if time permits.
Thanks, Dennis. Much appreciated. I don't see questions in the chat line, but to break the ice, I have a question for you. So you mentioned the pilot test that can increase the geotechnical resistance factor of 50%. However, we do not have the same, should I say, codified reward system for other geotechnical testing, maybe except for the Canadian Highway Bridge Design Code that introduce the degree of understanding of the geotechnical system. But do you believe that this is the way forward?
Sorry, Gennaro, you were coming in loud and clear earlier, but now you seem to be broken up, but I think I caught most of the words. Yeah, I think you were talking about the latest edition of the Canadian Highway Bridge Design Code, where we also got into consequence factors and the degree of understanding.
Hey, Duncan, just 1 second here.
Sorry, what's this? Dennis, can you hear me?
Yes, I'm here, but as I said, I'm having difficulty hearing you.
Yeah.
But yeah, the resistance factors I quoted there didn't necessarily reflect the current version of the bridge code, and it's important to consider your degree of understanding of the site and consequence of failure in those types of things. I think was what your question was about, but I'm not.
Well, yeah. No, so if you can hear me, my question was more to how to reward the effort and investment for other methods of geotechnical testing. So, for example, if I decide to do more lab testing, or if I decided to do more field testing, do you believe that the degree of understanding is the way forward to reward the practitioner in the kind of investment?
Yes. Okay. I think I heard you and understand your question. Yeah. I think, yeah, it's a very important feature. Prior to the introduction of degree of understanding in that, the resistance factor was sort of a single value and did not reflect the level of effort or understanding that a practitioner or designer may have. So the intent of introducing that degree of understanding was to improve the design process, but also to reward an owner who is willing to do more extensive site characterization, whether it's through more laboratory testing or in situ testing, to get a better understanding in terms of reducing the uncertainty or variability across the site. So I think I certainly, yeah, I agree that it's I think it's an improvement and a step forward, because I think it enhances and encourages better engineering.
I just encourage everybody, if there is any question, to type it in the chat, which is below the Zoom window. In the meantime, I have another question for you. That how do you promote, given that my feeling, my observation, the current practice is that there is a prevalence of very sophisticated numerical modeling in design, but how do you promote the use of geotechnical testing, given the ease that everybody has now to just run a finite element model? How do we make sure that especially the new generation understands that before running that model, maybe you, as you mentioned also in your lecture today, that we need to have a good geological understanding, a good characterization of the parameters. What can we do in terms of education especially for the new generations?
Yeah, that's an important point, Gennaro. You know, and I think in some cases the numerical modeling capability has exceeded some of our capability of producing or measuring the parameters that are required in the various models. So I think it goes to reliance of the designer and maybe the senior reviewer or more experienced people on engineers on a project to understand that if you want to use this model, then you either have to increase your sophistication of testing, or you have to calibrate it with respect to field performance, such as, let's say, piezometer response or slope, lateral deformation in the slope inclinometer. So in terms of matching field performance is key. A lot of the models, tend to see if they can match the results of stress strain curves from laboratory testing, and that's essential to do. But the raising it to the next level then is doing matching to in terms of actual field behavior, and then once you have your model calibrated to field behavior, then it becomes a very powerful tool.
Thanks, Dennis. I think it's interesting that we just went a little bit over time, but it was very interesting discussion about the importance of geotechnical testing, despite, as you said, all the models and that we have today, the understanding of the basic, the basis is essential for our profession. Thank you very much again for your time today. I know that you are a very busy man. Thanks for all those that joined from the South Alberta area and elsewhere in Canada. Thanks a lot. Stay tuned for the new events with the Calgary Geotechnical Society and those organized by the National Canadian Geotechnical Society. Thank you. Have a good day. Thanks.
Okay, and thank you, everyone, and my apologies for running over. Everyone have a good evening. Bye-bye.
Thank you. Bye.